here for those that aren't available. So we finished the unit on electronics last week, but we are still talking about energy and energy consumption. We're going to shift gears a little bit and talk about renewable and non-renewable energy. We're going to focus on renewable energy today. So let's jump right in here. Everybody should be working on getting logged into Nearpod. There's the class code. I have put it up into the chat. Please make sure you're on Nearpod. That will be your grade today. So I'm going to move over to the Nearpod lesson here in just a second. But I want you thinking about this. What is the difference between renewable and non-renewable energy? Think about what is the difference between renewable and non-renewable energy. And I'm going to put that up in Nearpod so you can answer directly into Nearpod. Where's it at here? There it is. Go ahead and put that directly into Nearpod. The difference between renewable and non-renewable energy. Let's see, who do we have on here? I see Brian. I see Kishay. Isaiah, I see Gorgeous, good. Tamia, I don't see you logged into Nearpod. Josh, I see you in there. Alan, I don't see you logged into Nearpod either. Nina, I see you in there. Danny, good. Hanif, good. Damar's in. Alea's in. Richard, I don't see you logged into Nearpod.
You see me now.
Jacoby. Oh, I see Tamia now. So those of you that have not been able to log into Nearpod, is there a reason that you haven't been able to log in? I see Julius is in Teams now. Julius, go to Nearpod, please, and get yourself logged in. And we're answering the question right now, what is the difference between renewable and non-renewable energy? Your grade today, your live session grade, is based on your participation in Nearpod. So if you are choosing not to participate in Nearpod, then you'll have to go back in and finish it at another time. But your grade is based on your participation in Nearpod. So let's see. Jacoby says renewable energy can be used multiple times and non-renewable is limited. What does this one say? Renewable energy is able to be continuously used, while non-renewable energy is a one-time use. Okay, I like that one. Renewable can be used over and over again, and non-renewable is something that's a one-time use and will eventually run out. That's good. That's good. I see 13 people in now. That's a little better. Still a few people not in. Still a few people who have not answered. So make sure you're getting an answer in there. For your grade today, I'm going to go back through and see who's been participating. Julian, if you could please go ahead and get yourself logged in to Nearpod. I put the link up in chat, so you should be able to log in. If you're having trouble logging in, you need to let me know so that we can fix it, because I don't want to have to give you a 0 for today's grade. Okay, I see a lot of people putting stuff in. This is great. This is great. One use versus multiple times. There's a lot of cool things we can say about renewable energy. Okay, you have a presentation up, because if you do, I can't see it. Brian, you should be logged into Nearpod. If you're logged into Nearpod, you should see the question that's up. I don't have a presentation. I just have that the Nearpod screen. But I can put up the presentation, but I'm probably not going to use the presentation much. I'm going to be more on Nearpod. But if you want to see, this is what we're talking about, the difference between renewable and non-renewable energy. Okay. But good question, Brian. It's all good. Okay, so we got 14 people in. Most everybody who's in has answered the question. Make sure you're answering the question. I'll give you a couple more seconds to do that. And let's talk for a second about the expectations for today. So if you're in class today, you should be doing the participation in Nearpod. And for your asynchronous assignment, I'm going to give you a specific assignment on Class Kick. So we'll get to that in a second. And I want to show you more slides on Nearpod. So I've got everybody who's in has answered that question. So let's talk about it. Renewable versus non-renewable. We throw that word around a lot, and I think a lot of you got pretty good answers on the last slide. If it is a non-renewable energy source, that means we're using it up. So like coal, natural gas, the big ones that we use for most of our energy right now are non-renewable, right? So that means we're running out of them. It seems like we might have an infinite amount of them, but that's just simply not true because we dig them all out of the earth. And as we know, the earth has a finite amount of those things. So there's been a real push right now to find renewable energy sources, right? Things that we can use that basically don't go away. Things like the wind, things like the sun, things like wave energy or hydroelectric power, things that we can use that we're not consuming while we do it, right? So if we're using wind energy, there's more wind right behind it, right? Wind has to do with the rotation of the earth and other things, so it's not going away. We're not using it up. It's still there even after we capture some of it. Solar energy comes from the sun. If we ever don't have the sun, then we've got bigger problems than having non-renewable energy. So the sun's going to always be coming down on the earth, and we'll be able to capture that via solar panels. Likewise with waves. Waves are generated based on the tides, based on the moon, based on gravitational forces, universal gravitational forces. So those are always going to happen, right? So we can harness some of that energy. And there are a lot of cool new innovations going on with all those things right now. So we'll talk about those over the next few days. This slide is an older slide because it doesn't even have wave energy in here, which is one of the newer forms. But I like it because it has both things right side by side, so you can kind of see it. Non-renewable things, we're talking about oil and natural gas and coal, and even nuclear is non-renewable because when nuclear fuel is used, and when nuclear fuel is used to make power, it is used up. It is transformed during that power production, right? So it gets used up. It's much cleaner than other things, than coal or natural gas, but it still is considered a non-renewable source. Okay. Any questions about that so far? Which one is electricity is like in the middle? So electricity is formed from either of these things, right? So electricity itself is not a source of energy. It is the use of that energy, right? So you have a power plant. Like the power plant near here run on some of them natural gas, some of them on coal, some of them on oil, and they produce electricity, and that electricity goes out over the wires and into your homes. In some places, they have power plants that are based on wind energy or hydroelectric energy, and those are producing electricity and bringing it out to your home. So that's why electricity is in the middle. Good question though, Leah. All right, so today we're going to focus on these four: solar, wind, water, and wave energy as sources of renewable energy. And I have some slides based on those, and then I'm going to ask you to do a little quick research project during the asynchronous time. All right, so solar panels. Solar panels use what's called a photovoltaic cell. Anybody seen solar panels on houses around here or anything? Yep. First period, we had a few people who had solar panels on houses in their neighborhood. Yep. So a few years ago, DC had an initiative, got some kind of a grant or something, where if you put solar panels on your house, you got some money back, or you got some money to help you pay for those solar panels, right? And what you're doing then is you're taking that solar energy and using it for your house, and then also feeding some of that power back into the power grid if you don't use all of it, right? So it's a good thing, and we've got a lot of sunlight around here in this part of the world, so it's good. Solar energy is good. Now the problem with solar energy is it doesn't produce a heck of a lot of energy, right? The solar panels that cover your roof may or may not produce enough power for your house, right? Depending on how much energy you use. And we'll talk about the energy consumption later and exactly how much is produced. So they're not super efficient. They're more efficient if you build them in places like the desert or in places where they get a whole bunch of sunlight, right? Toward the equator or something like that. They're more efficient there because they have more sunlight. But if you build them in some place like someplace that's cloudy all the time or someplace that has a lot of bad weather, they're going to be a lot less efficient and not worth as much time because they don't get as much solar energy. So I've also seen, if anybody would, next time you're out and about, take a look at like those parking meters that are all around DC, the ones where you have to put your credit card in order to pay for parking. If you look at those, a lot of them have solar panels on top of them, so they don't connect into the power grid. Right? So they have a small solar panel on top of them. They don't need any additional electricity. During the day, they use that electricity and then they store it in a battery for use when it gets dark or when it's cloudy. So I think that's a pretty cool application for solar panels. So let's talk about how a solar panel works. I've got a short video that'll come up in the next slide or two here. I want to talk about it briefly before we watch that video. Solar panels are made out of something called silicon. Silicon is a semiconducting material, which means it conducts electricity, but not as good as, say, copper or something like that, right? It's a partial conductor or a semiconductor. And the cool thing about silicon is that you can add elements to parts of it and make it either more or less conductive, or add electrons or take electrons away from it. So, for instance, in the solar panel, you add electrons to the top layer and you take electrons out of the bottom layer, right? So that makes sort of an electrical difference between the two. And then when the sunlight hits the top layer, it pushes those electrons out of that top layer toward the bottom layer, which accepts those electrons, right? Creating a flow of electricity. And that flow of electrons is considered to be electricity. So I think the video explains a little bit better than I do. But I wanted to speak about it briefly because the sound was not good on the video this morning. So I'm going to try it again. I've adjusted a couple things. So let me know if you can hear the video or not once we start to play it. I'm going to try it. Can you all see the video? I haven't started to play it yet, but let me know if you can see it. And then once I start to play it, I want you to let me know if you can hear it because I'm not certain that the sound will come through. So let me set the captions so even if you can't hear it, you'll be able to read it. I'm going to pause it. Were you guys able to hear that? No?
No, I couldn't hear that or see it.
I couldn't see it either.
Okay. Can anybody see it if you're on Nearpod?
No. It
No?
says eyes up front, the video play on your teacher's device.
Ah, okay. Hold on a second. Let me see if I can share it this way. I'm still getting used to how to do this correctly. Okay. Now I'm going to try it again. I'm experimenting on you guys as usual. I'm going to try it again. Tell me if you can hear it. Can you see it now on Microsoft Teams?
Yes, we can see it.
Okay.
You can't hear it.
Okay. Say it again. Can you hear it?
No.
No,
No.
can't hear it. Okay. I can't send you the link to watch it, Tamia, because there are questions embedded in it. And if I do that, then it won't capture that you are paying attention. So let me try this. Can you hear it?
No.
No.
I'm not liking this whole thing. Can you hear me talking?
Yeah.
Yeah.
Okay. Just watch through it, and then we'll talk. We'll talk. Just watch what it's doing. Okay. So, can you see the question up there? Does it give you the question on your Nearpod? Okay. Can you answer the question? What are solar cells typically made of? Magnesium, silicon, or rainbows? My daughter's here. She's pretty sure it's rainbows. Or she wants it to be rainbows. What is it? See some good answers in there. Most everybody's got it. It is silicon. So I'll back up just to see it. So the active. So silicon is an element. You'll hear about that whenever you have chemistry. Okay. Which type of material has the positive charge? N type, P type, or S type? Which type of material has the positive charge? Tamia is laughing at me. I'm not sure why you're laughing at me, Tamia. I'll work on figuring out the videos for next time. I'm not sure why you can't hear it. That's not really useful if you can't hear it whenever I play. Okay, most people got that. That's P type, so that's good. It's like maybe one person didn't answer yet. Two people maybe. All right, let's go ahead and move on. Okay, visible light is included in a spectrum that is usable by solar cells. True or false? Visible light. Yeah, Brian, I have my computer sound way up. True or false? Visible light is included in the spectrum that's usable by solar cells. Most people are going for true. That is correct. So visible light, meaning stuff that you would see, that you could see, can be used by solar cells, which is why if you shine a flashlight on a solar cell, you can produce electricity with it. Okay, so let me put this back in. Okay, so sorry that you couldn't hear that. I will work on figuring out why that happened and make it better in the near future. But let's talk about briefly for a second how that works. I'm going to go back to this slide here. So solar cells, as opposed to the other types of renewable energy, don't have any moving parts. When we talk about things like wind turbines and hydroelectric power, those are all generated based on a moving generator. The solar cell doesn't have any moving parts, which is why it's kind of a unique way of creating energy. And it just has these, I guess it has moving electrons, but not moving parts. And so it's energy created on a molecular level by pushing the electrons around from one place to another, and by building those places in such a way that they're susceptible to receiving or pushing out those electrons, right? So the solar cell is made from a specific type of material and treated in a specific way to force the electrons to be moved by the sunlight, right? So the sunlight exerts this pressure on the electrons and moves them from one place to the other, and that movement of electrons is what we know as electricity. Right, so it's kind of an interesting way to produce electricity. Anybody have questions about how solar cells work before we move on to the next part?
I just wanted to know if you could send the link and we could watch the video, like after class maybe.
Yeah, I can send the link for the video. Now the video itself, the one that I used, is a YouTube video, and it was a lot longer than the 4 minutes that we used here. So I think it's 10 or 12 minutes long, but I'll find that link and shoot it over to you so you can watch it. Okay, so wind turbines use a coil of wire to create current. So you've all seen electric motors, even small electrical motors. I'm not going to watch that video. Small electrical motors, like for instance, like this one, that something in the middle is turning around, spinning around based on electricity that is put into it, right? You can run that motor in reverse by putting mechanical energy into it and create electricity from it, right? So it basically runs it in reverse. So a motor with something like a electrical, some small toy or something that you have, or even a blender that's got an electrical motor on it, or something else that's got some sort of a electrical turning force on it, electrical motor that turns around on it. If you twist that motor back in the other direction, what you have is a generator, right? So you will actually move electrons back through the other way. And the way that it does that is it uses a coil of wire. I'm going to go back to the other picture because it's easier to see here. This coil of wire rotates around and through a magnetic field. And I think we talked about this last week at some point. A magnetic field will move electrons in a conductor. So if you put a piece of wire in a magnetic field, it will line up the electrons, right? And it will start to move those electrons based on the magnetic field. And because electrons are electrically charged particles, right? They're negatively charged particles. So they will move when they're inside of a magnetic field. The magnet will essentially move those electrical particles. So if you have this rotating coil of conductor, this copper or some sort of conducting material that's moving really fast through a magnetic field, it generates a flow of electrons or an electrical current. And the way that most generators work is that they have multiple magnetic fields, so that as the thing spins around, it's going through multiple magnetic fields very, very quickly and creating current in a lot of different places. And that's called a three-phase motor, and we can talk some more about that as we get further into it. But basically, that's what's happening in the other types of renewable energy sources. They have a motor that's being turned by some sort of a renewable energy, being turned by the wind, being turned by water, or being moved in an up and down fashion by the waves. So this is what a wave energy motor looks like. It's not really a twisting motor like you're used to. It's an up and down motor. And so it's got sort of this plunger that goes back and forth between the coil winding, or around the coil windings, so that it's producing this electrical current as the plunger moves in and out of the coils. So as these waves come through this this area here, they move these plungers up and down, and those coils pass back and forth through the magnetic field, producing a current every time that they move. All right, I'm going to show you one more thing, and then I'm going to open it up for some questions. Can you all see this simulation? Yeah, okay. So this is a very basic simulation of what might happen in a typical motor. So I have a magnet here that I can move around, this north-south magnet that I can move around. And if I put it inside this electrical coil here, you can see that as I move it, it creates an electrical current through that wire. And that's because the magnetic field is pushing those electrons through the wire. So even without touching them, I can show you what the field lines look like. So this would be sort of the magnetic field associated with this magnet. You all played around with magnets before. You know that as you get closer and closer to the magnet, it gets more and more attractive, more and more sticky. Right? So if I get something metal that's closer and closer to a magnet, at some point the magnet will pull it out of my hand and it'll get stuck to it. And that's based on the strength of the magnet. So as I move this magnet in and out of the coil, I can see that these force lines here touch the coil, and they're moving the electrons as I get this magnet closer and closer to the coil. Now the other thing you'll notice is if I stop the magnet, it stops producing electricity. So the magnet actually has to be in motion back and forth this way through the coil. Okay? So as I'm moving this magnet back and forth through the coil, it's creating a lot of electricity. If I have it way up here, it still creates some electricity, just not as much. It needs to be where the magnet is producing the most electricity closest to the magnet, where the coils are closest to the magnet. So this is how that wave generator and that turbine generator work. This magnet is moving very, very fast through these coils and generating electricity as it does so. The other thing I want you to notice is if I move it this way, the voltage is high negative while the negative part of the magnet goes through. And as the positive part of the magnet goes through, it creates this high positive voltage. Okay, so I'm going to stop talking here for a second and open this up to questions. Anybody have questions about how these generators work? And I know I've given you a lot of information, but I'm going to share a couple of videos with you so that you can get some better information. Any specific questions? No? Okay. All right, so your asynchronous assignment today is to do a little research for me. And what I want you to do is I'm going to give you specific websites. The third period class kit code is right here, Y3E CBG. And I'll go ahead and link that in. I'll show you what class kick looks like so you can actually see what I'm expecting from you. Shouldn't take you very long to do. Go here. So what I'd actually like you to do is to go in here and so in the class kick assignment, you'll see several slides here, but they're not a lot of work on each of the slides. Just click the link here. So for instance, this one is solar energy. And it says in each one of these articles, what are the pros and what are the cons of using solar energy? I want you to come up with 3 of each, 3 pros and 3 cons that you feel are most important. There's no right or wrong answers here unless you don't do it. If you don't do it, I can't give you credit for it. So come up with 3 pros and 3 cons, things that you think are most important, pros and cons for solar energy, and move on to the next one and do the same for wind energy, same for hydroelectric, and same for wave energy. And then in the last slide, what I want you to do is based on your research, based on what you have figured out, which of these type of renewable energy do you think is, quote, better? Right? Decide which one you think is the best of the 4 types of renewable energy. And we'll use that information tomorrow as we have our discussion. Okay, does anybody have questions about what I'm asking you to do?
Yeah,
Yes, Jacoby?
what's the name?
Say again?
The name of the website.
ClassKick?
Class.
ClassKick.com. Let me just get a full link here and I can period. I'll copy the link right here and you can just click it. That is going to be all for today. I will link those videos into the Canvas assignment as well as the recording of today's session. So I'll link them right into the live assignment for today. Your live assignment for today is to have participated in the Nearpod assignment. If you missed out on that, I'm going to link a student version of the Nearpod assignment in so you can go in and do that link yourself and do that those activities on your own. But yeah, that is all I've got for you today. I'm going to end a little bit early today. You're welcome. Anybody have anything they want to add or ask?
We do all 5 pages.
Yes, do all 5 pages. We've got like 5 minutes left in class, so if you want to work on them now, you can probably get them done pretty quickly. Nina's got her hand up. Yes, Nina.
Do you want us to like explain like for the pros and cons or just put them in there?
I'm going to ask you to explain next time.
Okay.
So just put them in. If you want to put an explanation in there, that'd be fine. Tamina, you got your hand up?
Yeah, what was the day that we had to submit the 2 pictures of the circuit? Was that Thursday or Friday?
2 pictures of the circuit. Let me look on Canvas. I honestly don't remember. Let's see. Thursday would have been the 12th. Friday would have been the 13th. Let's see what we got here. So you had we did that on the 13th. That was Friday. You can submit it on the 12th if you want, but you should have 2 pictures of circuits submitted for the 13th for your multi-sim circuit.